Hey, everybody. Welcome to our third and final installment in our voting lessons. We're going to take on a voting system that's a little bit different than the one we've talked about previously with our ranked choice voting and stuff like that. This is going to concern what we call weighted voting. And we're going to look at both that system and also talk about a very important thing within that system, which is how do we define power in a weighted voting system. So the one you're probably the most familiar with, especially if you're from the US, is the Electoral College. That is a weighted voting system, right? Each state has a certain number of electoral votes granted to it. And so each state doesn't quite hold the same sway when it comes to the Electoral College. Places like Rhode Island or Montana, right, relatively small or relatively low population, are not going to carry the same number of votes as a Texas or a California or a Florida or a New York, something like that. So this is what we would call a weighted voting system. And we can break down some terminology here just to make sure we're all on the same page. While this can be used in a variety of different applications, we're primarily going to use it with the following terminology. So we're going to have what we call a motion, which is just a yes or no vote between either two candidates or two alternatives. So you can think of this as a terms of in a Senate or a House of Representatives or something like that. A motion would come to the floor, and then everybody would vote yay or nay, yes or no, right? And that would either pass the motion or fail the motion, depending on how many people you needed to pass that. Now, the players in our voting system are going to be the institutions or the individuals that hold a certain number of votes. So in our electoral college, the players are the states. They are the things that hold a certain number of votes. So Florida would be a state, Alabama would be a state, California would be a state, Oklahoma would be a state, so on and so forth. That these are all players is what we think of. So in something like the House of Representatives in the U.S., uh, the players would be the different individual representatives. Um, and so the main difference here between what is happening in a weighted voting system and what we've done previously is that previously you just got one vote. All the voters got one preference ballot, and we combine that into a preference schedule. Here, one single player may control many different votes. So in order to do this, we name our players the following way. So we're just going to use a capital P to represent the player, and then we're going to index them here in the subscript. So 1, 2, 3, 4, 5, all the way up to however many we have, where this capital N is just how many players we have. So the actual weight in our weighted voting system comes down to how many votes a certain player controls. And so we're going to denote that in a very similar way. We're going to use lowercase w to indicate the weight, and then the same index as the player. So player one will have a weight of W1, player two will have a weight of W2, so on, so forth. Right. So we're going to list the players in order of weights from highest to lowest. Right. And the main thing we're looking for here is how many votes do we need in order to pass a motion? Right. So we'll call that our quota. It's the minimum number of votes we need to actually pass the motion. Now, the way we can describe this is actually pretty simple. We're going to list our players in order like we did of their weights. So we're actually not going to put the player there. We're not going to say player one, player two, because since they're in order, we kind of know this is the first one, this is the second. We're just going to list their weights out. And then we're going to put our quota over here. So the whole thing will go in these brackets. We'll have whatever our quota is, whatever that goal line is we need to hit in order to pass our motion, a colon, and then we'll list out the weights, right, in order of the players, which is going to be from highest to lowest. So here's an example of one like that. If we have a motion in the following weighted voting system, we would need 13 votes to pass this. And we have 4 players here. One has 12 votes, one has 6, the other one has 6, and then the last one has 1 vote. So one of the big questions we're going to ask when it comes to these kinds of voting systems is what combination of players could pass this motion? So for example, right, if this person with 12 votes, so player 1 and player 2 both vote yes on our motion, that's 18 total. power between them, right? That's 18 total weight, and that would be bigger than 13. So that would pass it, right? So we're looking to hit exactly 13. If we hit 13, we're good to go. So ties in this case actually work out for us. Our quota is going to be equal to or bigger than whatever we need. So player 1 and player 2 pass it. By the same logic, player 1 and player 3 would also pass the motion if they voted yes. And even player 1 and player 4, if they both voted yes, would pass the motion. Player 2, if they vote yes, and player 1 votes no, the only way to pass the motion is if 3 and 4 actually vote yes. So our combinations here, 1 can't pass it by themselves. They need somebody else. So 1 and 2 would pass, 1 and 3 would pass, 1 and 4 would pass. And then a combination of 2, 3, and 4 would also pass. That would add up to 13. Doesn't look like there's anything else here that'll end up passing this motion. So when it comes to weighting voting systems, there's a couple of quick and easy rules we have for setting the quota. One, quota should not be more than the total of all the weights, because if it is, then you can never pass anything. Another one is that the quota should represent a majority of the total weight. This kind of goes back to what we talked about before with our fairness criteria, where we have the majority criterion and stuff like that. If we want to set a quota, we don't want to set it so that the majority can vote against something, but it still ends up passing. So we generally want the quota to represent a majority of the total weight. And this one's a bit interesting, this last one. So Q should be set to the weighted voting system matters. What this means is that we want to set it in a way where the distribution of the weights and the players are actually meaningful. For example, if we have this set up here, where we need 19 votes to pass something, and we need 8, 7, 3, and 2 in terms of our players, if we do 8, 7, and 3, that adds up to 18 total. So the only way to pass this would be if all 4 people vote yes. So really, having this person have 8 total votes and this last person have 2 total votes doesn't mean anything, because the only way something's going to pass this is if all 4 people vote yes. So really, that's the same as this system here, right? Where we have a quota of 4 and each player has a weight of 1, right? So in this weighted voting system, it looks really complex, right? But really all we're doing is disguising the fact that in order to pass something, we need everybody to say yes. So a couple more terms to look at. A player whose weight is bigger than the quota is called a dictator. That's because if they vote yes on something, then they automatically are going to pass it. And if we follow rule number 2 here, and the quota represents a majority of the total weight, if they vote no, well, they have a majority of the total votes. So if they vote no, it's going to be a no. So in that case, the rest of the players end up not mattering. So for example, here, right, this person here, this first player, has a weight of 6, and it only takes 5 to pass. So if they vote yes, something's going to pass. If they vote no, there's no way player 2 and player 3 can add up to 5. So they're not going to get anything done. And in that case, we call the other 2 players, right, a dummy. That is a person whose vote never matters, right? So whether or not they vote yes or no is irrelevant to the outcome. So in this example again, right, whatever 6 votes is going to happen, 2 and 1 in this case are players 2 and our player 3 with a weight of 2 and a weight of 1. Those are going to be dummy voters in this case, where it really doesn't matter what they say. Here's another example of that. We have not a dictator here, right? But we have 10, 10, 10, and 9, and our quota is 30. So the only way this thing's going to pass is if player 1, player 2, and player 3 all vote yes, right? Player 1, player 2, and player 4 can all vote yes, but that only gets us to 29. So we need that last person. But if these 3 vote yes, then that gets us to 30. So in this case, it really doesn't matter what player 4 does here. Really, we're just looking at the first 3 people here, player 1, player 2, player 3, and whatever they decide is going to end up being the actual outcome. So let's take a more realistic example here, right? We have the US Senate with 100 members, right? And recently, this was a few years ago, we had 53 Republicans, 45 Democrats, and 2 independents. Now, there's a couple different things that happen in the Senate when a bill comes to the floor. First, we have a motion to proceed, which is typically given by unanimous consent, where we just say, is anybody okay with this going, and everybody's like, aye, and then they start talking about the bill. This one's probably the bigger one, cloture, which ends the debate, and that requires 60 votes. So in order for the debate to end, 60 people have to say, like, okay, I've heard enough, I'm ready to vote on this thing. And then we have our final vote, and that just happens by a simple majority. So in this case, with 100 members, a simple majority would just be 51 votes. Right. So what are the weighted voting system summaries for these different votes? And we're going to make an assumption here that all of our Republicans are going to vote the same, all of our Democrats are going to vote the same, and all of our independents are going to vote the same. Obviously, that is not necessarily a realistic solution, but we're going to simplify it a little bit just so we can kind of understand this. So go ahead and pause the video here, see if you can come up with this. I will post the answers to this to Canvas, but we'll see an answer to one of them a little later on in the video. So take a crack at this, see if you can figure out what these would end up being. Now, the question that comes as a part of this is who has the greatest share of power in each type of vote? So who is the most powerful player? Not who has the most weight, but who is the most powerful? All right, so that's a very different question here. Now, there is also a situation in the Senate where you can have a treaty, and that has to be ratified by 2/3 of the vote. So that is 67 senators or more in favor, right? If you do a weighted voting system for this, is that similar to any of these up here, right? Especially with our weights of 53, 45, and 2. Can you see any similarities there? So take a minute, answer these questions for yourself, see if you can come up with it. And now that you've done that, right, let's switch it up a little bit. So let's suppose hypothetically that after an election, we get the following distribution: 49 Democrats, 48 Republicans, and 3 independents. Now, we're going to, again, use the same assumption, right, that all Democrats are going to vote the same, all Republicans are going to vote the same, and all of our independents are going to vote the same. So in that case, we'll let player 1 be the Democrats because they have the most votes, right? Player 2 would be the Republicans, they have the second most votes, and then player 3 would be the independents, they have the third most votes. So go ahead and again, try and write out this weighted voting summary here. And then based on this, which party do you think has the most power? Well, a good question to answer this would be looking at what combinations of players can pass a motion in this case. And so if we just go off of our simple majority, right, where we're just trying to actually pass a bill or pass a motion, we need 51. We need 51 total senators. So the Democrats can't do it by themselves, the Republicans can't do it by themselves, and our independents can't do it by themselves. Now, if the Democrats and Republicans vote together, that would get us 51. That would be good. If the Democrats and independents vote together, that puts us up to 52. That's also good. That's 51 or more. Even the Republicans and independents, that would put us up to 51 as well. So we're good there. And then, of course, right, if all 3 of them vote for something, then of course it's going to pass, right? Nobody's voting against it. So what we can do is write out these different scenarios. We call a group of players that band together to vote the same way a coalition, right? And so these would be our winning coalitions. So every combination of players that could actually pass a motion here. So we have, of course, all 3 voting the same way could pass a motion. The Democrats and Republicans voting the same way could pass, the Democrats and the independents, and the Republicans and the independents. So these are all our possible winning coalitions, right? This is every combination of players that could pass a motion. So let's look at a power index for this. Now, a power index is just a way to assign a number to how powerful we think a certain player is in this weighted voting system. So this is going to represent their share of the overall power. So if we imagine we start with a power of 1, right, and then we break that up amongst our players into a bunch of fractions, right, then we'll get what we call a power index. And it's just going to look like parentheses and then the powers of each of the players, again, in descending order. So player 1, player 2, player 3, so on and so forth. So 1 half, 1/4, 1/4. That's totally a cool power index. Player 1 would have half of the power. Players 2 and 3 would each share a fourth of the power. And this is a valid power index because all of these together add up to 1, right? We're splitting up the total power, so we want all of it to add up to 1. This one could not be. This does not add up to 1, so this could not be a total power index. So an easy way to do this, let's look at our winning coalitions again for our hypothetical US Senate. If we count how many times each player appears in a winning coalition, right, then we could make that into a power index, right? So we would just want to count up how many different letters we have in here. So we have 6 here and 3 there, so that would be 9 total. And then I'm going to look at how many times each one appears. So the Democrats, 1, 2, 3. So that would be 3/9. Republicans appear 3 times as well. So that would be 3/9. Again, the 9 coming from every possible letter here, right? We have 9 total letters. And then the independents actually appear 3 times. So even though we have a scenario where the Democrats are technically in power with 49 votes, the Republicans are one behind them at 48 votes, and then the independents have only 3 votes. By this power index we have, all of them have a power of 3/9 or 1/3, right? So they all have an equal amount of power. Okay, well, maybe that's just not telling the whole story. Maybe that wasn't the right way to look at power. There's a more sophisticated way to go about this, and that is what we call the Banzhaf power index. I'm going to say Banzhaf as many times as I can because it's very fun to say. So this was a law professor at George Washington University named John Banzhaf, who used this index in court cases. Now, I don't actually know the context of this, but if you were in my social justice math class, this might be a fun project topic to look at how exactly this was used. So we're going to abbreviate the Banzhaf Power Index by BPI, and that is going to measure each player's ability to cast what we call a critical vote. So let's talk about what that means. So first off, a critical player is one who, if they're in a winning coalition and then they leave it, that coalition stops being a winning coalition, right? So their presence is necessary in order for that coalition to actually pass the motion. And if a player can change a winning coalition to a losing coalition by taking their vote away, right? So if they are a critical player, then we call that vote a critical vote. So the idea here is just we look at how many times each player is critical to a winning coalition, right? Because if you're in a winning coalition and you could suddenly decide you want to change your vote, but then you still end up, right, the people left over still have enough to pass that you weren't really that important to begin with. But if you up and leave and then all of a sudden they don't have enough votes to pass, well, they really need your votes, right? So this is the idea behind this Banzhaf power index. So we're going to look at how many times a player is critical. And what really helps is writing out this chart here. So this is actually our weighted voting system from our hypothetical Senate before. So if you wrote this down last time, well done. We have 51 total votes needed to pass. That's our quota, so a simple majority here. We have 49 votes for the Democrats, 48 for the Republicans, and 3 for the independents. Those are our weights. And we know what our winning coalitions are from earlier. So we have a winning coalition with all 3 parties, a winning coalition with the Democrats and Republicans, a winning coalition with the Democrats and independents, and then a winning coalition with the Republicans and independents. Right? And we can count up the number of votes that each one would get, and we can see, in fact, they do hit the quota each time, right? Even here where we tie the quota, that's enough. So let's look at the critical players in each case. Well, there's no critical players in this first one, right? Because if the Democrats leave, the Republicans and independents can still pass. Okay. If the Republicans leave, the Democrats and independents can still pass. And if the independents leave, the Democrats and Republicans still pass. So if one party leaves this coalition, it's actually not going to affect the outcome. The motion is still going to pass. However, down here with our Democrats and Republicans, if the Democrats decide to leave this, the Republicans are left by themselves and they only have 48 votes. So they can't hit that 51. So the Democrats are going to be critical here. And by that same logic, the Republicans are also critical in this coalition, because if they leave, it leaves the Democrats by themselves, and they only have 49, so they can't hit 51 either. So in this case, both the Democrats and the Republicans are critical players here, right? They're casting critical votes in this coalition. And we can use the same logic down here, right? In both of these, if either party leaves, right, suddenly that ceases to become a winning coalition. So in this second one, both the Democrats and independents are going to be critical as well. And then in this last one here, the Republicans and independents are both critical as well. So each party ends up being critical twice in this scenario, and we have 6 total times where we have a critical vote. So what we're going to do is 6 is going to be our bottom number, and then we're going to count the number of times that each party was critical. So we have 6 total, right? That goes on the bottom. Democrats are 2, so they get a 2. Republicans get 2, goes here, and then independents get 2. So again, we end up with 1/3, 1/3, 1/3. So same as what we did before with our just simple power index. Okay, well, let's go over this in general now that we've seen an example, right? So to get a player's BPI, or Bonsoff power index, right, we would count the number of times that each player is critical, right? And we would call that number B sub I. So we're going to make some new variables here. Don't let them confuse you, right? The process is exactly the same as over here. It's just when we're talking about it in a general sense, we have to have variables here to represent what we mean. So if player 1 is critical 3 times, then B sub 1 would be 3. All right, so we're going to count that up. That is not our power index yet, right? Then we have to add together all of those. If we go back, that's the amount of times that anyone was critical. So last time that was 6, right? So that would be our bottom number here. And then what we're going to do is we're going to take the number for each player, so the number of times each player was critical, put it over the total, right? And that gives us our Bonsoff power index. And so we have our Bonsoff power distribution, right, listed out like this: player 1, player 2, all the way up to our last player. And again, an easy way to check this is make sure when you add all these up, it adds to 1. If it doesn't, you've done goobered. Something is wrong, right? It has to add up to 1. Okay, so let's look at the Bonsoff power distribution for this weighted voting system. So we have a quota of 6, and then we have 4 players: a 3, a 3, a 2, and a 1, right? So weights of 3, weights of 3, weight of 2, weight of 1. So we're going to list out all the possible winning coalitions. Now, in these problems, this is what's going to take you the most time, and you are going to, at some point, miss one, right? So make sure you pay attention in this step, right? The way I do it is I literally just write down every possible combination and then cross it out if it isn't a winning coalition. So if you do that, of course, if all 4 vote yes, that would be 3, 6, 8, 9 total votes. That's more than 6, so that's good. Player 1, player 2, and player 3 is also a winning coalition. That's 3, 3, and 2, right? So that's also good. Player 1, player 2, and player 4. So 3, 3, and 1 gets us to 7. Player 1, player 3, player 4. You kind of see how this is going, right? Then what we're going to do is we're going to look and see who the critical players are there. So let's take this second line here, because none of them are critical players in the first one. So let's look at this one. Well, if player 1 leaves, that leaves us with player 2 and player 3. So 3 plus 2 is 5. That's not quite 6. Okay, so we need player 1 in there to pass this motion. If player 2 leaves, right, then we would have player 1 and player 3 left over, and that would be 3 plus 2, 5. Still not enough. Okay, so player 2 is also necessary. What if player 3 leaves? Okay, if they leave, we have player 1 and player 2. So that's 3 plus 3, which is 6. So that would actually still pass. So player 1 can't leave, player 2 can't leave, but player 3 can, right? Player 3 is not super necessary here. So our critical players are player 1 and player 2. Player 3 can leave, right? And we would still pass the motions. Their vote's not critical here, right? We repeat that process and we get all of the times we're critical here. So player 1 appears 1, 2, 3, 4 times. So they get a 4 for B1. Player 2, 1, 2, 3, 4. So they also get a 4. So B2 is 4. Player 3 is here and here. So that's just twice. So they get a 2. And then player 4 is here and here. and they're also just twice, they get a 2. Add those all up, we get a total of 12, and then we just take each number and put it over our 12. So player 1 is 4 over 12, player 2 is 4 over 12, player 3 is 2 over 12, and player 4 is 2 over 12. And we can reduce those fractions down to 1/3, 1/3, 1/6, and 1/6. So an interesting thing to point out here, right? Player 1 and player 2 have the same weight, so it makes sense they would have the same power in this voting system. Player 3 and player 4 do not have the same weight, right? Player 3, the one with a weight of 2, right, has twice as many votes as player 4, but they end up having the same power by this. So are these weights accomplishing what we intend, right? And a way to look at that question is, how does our Banzhaf power distribution compare to the weights? Or even if we use the other way of finding power, right, how does that compare to the weights? Okay, well, a way to look at this that might be a little easier to see, right, because we have fractions for our Banzhaf power distribution, and we have whole numbers for our weights, right, is using relative weight. And so all we're going to do here is just add up the total weights and then put the weight for each player over that. So if I add up the total here, I get 9. So I'd have 3 over 9, or 1/3, 3 over 9, or 1/3, 2 over 9, and 1 over 9. So what this does is it puts our weights into a fraction, so it makes it easier to see how they compare. So we have 1/3, 1/3, okay, there, and then we have 2/9 and 1/9, where we have 1/6 here and 1/6 here. So looking at this, right, what can we conclude? Well, the first two, their weight appears to be the same as their power, right? So that's a good thing, right? That means the weights for the first two are accomplishing what we intended. However, here, player 2, like I said, is supposed to be, or player 3, I'm going to keep doing that. Player 3, right, is supposed to be twice as powerful as player 4 here, right? They have 2 votes, player 4 has 1 vote, but they have the same power, right? So different weights, same power. So that tells us that maybe our weighted voting system here isn't quite accomplishing what we're hoping for it to do. All right, so an example, if you'd like to try this again, compare our Banzhaf power distribution and our relative weight distribution for this weighted voting system and see what you can come up with. All right, well, that is it for this lesson. There's a lot of stuff buried in here, so I would strongly recommend going back and looking at this if you're in my class, right? Try and work out some of these examples on your own. I know that takes time. I know that's difficult to do, especially if you're not a self-starter, but the more you actually try and work on these yourself before you start working on the worksheet and things like that, the better it's going to be in the long run, the more this is going to sink in. So spend some time with this, right? We have a couple different things happening here. We have our weighted voting. We have a couple different power distributions. Of course, one of them is more fun to say than the others. I'm not going to say which one. That will be up for you to decide, but a lot of information here. So spend some time with it, right? And then when we come back, we will talk about a very new, very exciting, different chapter in our social justice math journey. So thank you for your time, and I will see you in the next one.